All right, so tonight let's start with something we don't always hear about when discussing environmental issues. Some good news. We've made tremendous progress on urban air quality over the past half century. This is visually evident when we look back at the air quality of old in America's oldest, largest megacities. And it is one of our biggest success stories. The increasing frequency of clear skyline views and distant mountains are poignant reminders of not just our progress, but our capacity to tackle challenging environmental problems. Now, these historical gains were achieved through coupled technology and policy focused on combustion-related sources, including motor vehicles, power generation, and heating. Now, at present day, despite these major successes, air pollution remains at levels of concern in many parts of the country, not to mention the world. And as we saw in the opening video, a changing climate introduces new challenges. For air pollution, the challenge of achieving healthy air for everyone is evolving within a complex, interconnected atmosphere. So as a research community, it's incumbent on us to dive deep, to build a comprehensive understanding of these challenges, and not just do this in real time, but under future climate scenarios as well. So to do this, my team and I are developing new types of instrumentation, projects, and collaborations that are enabling us to get a clearer picture of the air quality challenges we face. So at times, this changing world provides us with valuable opportunities to learn from natural experiments. So in that sense, my lab does not stop at the threshold of campus, but extends to New York City, where two recent projects illustrate how much we can learn from the dynamic world around us. In New York City and other major US megacities, we're seeing that the dramatic reductions in emissions of air pollution from combustion-related sources have changed the mix of reactive chemicals emitted to the atmosphere. We're shifting away from an era defined by motor vehicles to a diverse mix of sources spanning from cars to consumer products and beyond. So the first of those natural experiments, the COVID-related economic shutdown in 2020, brought a dramatic air quality experiment to New York City with empty avenues that simulated full-scale vehicle electrification. This caused a substantial reduction in reactive chemical emissions to the atmosphere, but I was more surprised by what happened the next spring. 2021 brought a return to normal human activity levels in the city, and also an anomalously warm spring that stood in stark contrast to the weather during the shutdown, with increases in airborne concentrations of reactive chemicals that exceeded the potential emissions reductions that were simulated by the shutdown. So while vehicle electrification still has huge benefits for reducing greenhouse gas emissions, this taught us an important lesson that future policy-related gains in urban air quality risk being offset by increased emissions of reactive chemicals in a warming climate. So now in another recent project, my team and I examined the effects of increased temperatures during the summer and extreme heat events on concentrations of suspended particles that are a fraction of the size of the thinnest human hair and among the pollutants of greatest concern. So using our measurements from two sites in Manhattan and Queens, we observed clear temperature-dependent increases, including during a multi-day heat wave. Now, these organic particles present a stubborn challenge for air quality that will be exacerbated by continued climate change and extreme heat events. And the underlying causes are not simple, but involve a fascinating combination of emissions from humans and plants, changes in atmospheric chemistry, and weather, all with major connections to energy, climate, and air quality-related policy. So we've learned some important lessons thus far, but we're not stopping there. Summer 2022 and 23 brought a flurry of activity stretching from Manhattan and Queens to coastal Connecticut, with my team coordinating large groups of collaborators that were visiting at highly instrumented ground research sites. And the action extends well past summer 2023, with our long-term measurements in Queens, accompanying a network of 12 other sites that are involved in an enhanced network that is growing around the US. These continuous measurements have already proven valuable for catching the 2023 Canadian wildfires and their dramatic impacts on air pollution and in rich chemical detail to probe their chemistry and human health effects through multidisciplinary science at Yale. However, we're not just thinking about today's problems or the problems of a dynamically changing world. And one of the most impactful things we can do at Yale is to train future generations of researchers and leaders. This is why mentoring and training emerging scientists is so central to my work, and why I involve our undergrads at the forefront of science, training them on advanced instruments and pressing questions. Now, these undergraduate research experiences are not limited to short-term summer holiday experiences, but sustained multi-year engagement as key teammates on major projects. So whether it's helping to launch NASA weather balloons from the Yale Coastal Field Station or analyzing complex streams of data, these opportunities often connect Yale undergrads to leading researchers in the field, working on the problems of today and tomorrow alongside principal scientists from companies, governmental organizations, and top academics. So, undergraduate education cannot stop when we exit the classroom. And Yale has a critical role to play, not just in understanding and addressing climate change, scientists, engineers, and innovators as the leaders of our shared future. Thank you.